For most people, any number that you can think of is a real number. For example, 0, 1, 2, -50, the square root of 2, pi. These are all real numbers. Now, there are a few rules that all of these real numbers follow, and we call them axioms. For the most part, the real number axioms are pretty straightforward. Like if you add two real numbers together, the result is a real number, and so on. The one axiom that sets these numbers apart from other sets of numbers is that each real number has a unique multiplicative inverse. It sounds cool, and once you understand what that is, you can use it at the dinner table to impress friends and family. Or not. I'll write all the real number axioms in the description. All of this talk about real numbers really begs the question, why are we bothering to say real? Are there numbers that are not real? Is my whole life a lie? The answer is yes. There are complex numbers. Imagine you're driving down a straight highway that goes on forever in front of and behind you. The road doesn't even go up and down, it's just flat. This is the constrained world of real numbers. Complex numbers are like taking away these constraints. With complex numbers, you can now travel side to side and you can definitely enjoy the scenery. Unfortunately, we already use the convention of writing real numbers like this. So we're going to need new notation to write down complex numbers. Enter the imaginary numbers. Yes, I did just say imaginary numbers. Before you think I'm completely crazy, just hear me out, okay? So maybe somewhere in your distant past, a teacher once told you that you may never, ever take the square root of a negative number. Maybe you even tried it once, and you brought shame to your family. Well, your teacher lied. You can take the square root of a negative number, you just need a new definition. Everyone, this is the imaginary unit. Imaginary unit, this is everyone. It even has its own happy little name, I. The poor little thing doesn't quite fit in with the real numbers, however. Well, forget them. We're going to define our own number line. Starting with I, we're going to say that if you multiply I with any real number, then the result falls along this line, which is at a 90-degree angle with the real numbers. This line is the imaginary axis. Now, a complex number is a real number plus a multiple of the imaginary unit. Here's 5 plus 4i. The real part goes on the real axis, and the imaginary part goes on the imaginary axis. When you add two complex numbers, you just add the real parts and the imaginary parts separately. In this way, we have 1 plus 4i plus 2 plus 3i is equal to the real part, 1 plus 2, plus the imaginary part, 4 plus 3, to give us an answer of 3 plus 7i. Maybe the strangest thing about the complex numbers is that they obey all of the same axioms as the real numbers. So the multiplicative inverse of 1 plus I is 1 over 1 plus I. I don't even want to begin to explain how to do division with complex numbers, and in fact, there is a simpler way to do it, but we're going to have to go through a little bit of pain to get there. So you've been doing mathematics again? Don't judge me, Kyle. In order to write down complex numbers in a more convenient form and be able to multiply them more conveniently, we're going to have to shift our perspective. This has seemed less convenient at first, but if you'll bear with me, there is a payoff at the end. Let's take this number, 3 plus 4i. Now let's imagine that there's a straight line going from the origin, the point 0 plus 0i, to our complex number 3 plus 4i. Conveniently, this line has length 5, and I'm going to give it the name h, which will be short for its full name, hypotenuse. The angle formed between this line and the real axis is roughly 53.13 degrees. And we can draw a couple more straight lines to form a triangle like this. Okay, now let me see if I can reach back into your mathematical past without inflicting any further trauma. Remember SOHCAHTOA? Well, those are the rules for dealing with triangles in situations exactly like the one we're in right now. The adjacent part of our triangle is the real part, and it's 3. Then since cos of an angle is the adjacent over hypotenuse, we get that cos of 53.13 is about equal to 3 over 5. Multiply both sides by 5 and you have 3 is roughly equal to 5 times cos of 53.13. Now, the opposite part of our triangle is the imaginary part, and it's 4. Using sine of the angle is equal to the opposite over the hypotenuse, we now have sine of 53.13 is about equal to 4 over 5. Again, multiplying both sides by 5, you get 4 is equal to 5 times sine of 53.13. So then 3 plus 4i is equal to 5 cos of 53.13 plus 5i sine of 53.13. That's not better. That's worse. Way worse. Before I show you the upside of this, here's a little leap. You can do this for any complex number of the form a plus bi. First, make a straight line from the origin to your number. Track the angle the line makes with the real axis, give it a name like theta, and track how long your line is. This is the hypotenuse. Give that a name like r. Then you just plug the numbers into the formula, r times cos theta plus ir times sine theta. Since r is common to both terms, you can factor it out to get r times cos of theta plus I sine theta. Now, thanks to the great mathematician Leonhard Euler. Euler? Yeah, Euler. Is he from Edmonton? No, it's German. No, he means Euler. No, I'm saying Euler, that's what I mean. Oh, Edmonton Oilers. No, Edmonton Eulers. Tight. Could go all the way. Team of the future. Or the past. And the present. Or both. It's Euler. Anyways, thanks to Euler, you can write cos of theta plus I sine of theta in the Euler form, e to the power of I theta. So, now you can write a complex number as r times e to the power of I theta. It's Euler. You've been so patient with me, so here's the upside. Multiplying exponentials follows this rule. The result of multiplying two exponentials is that their exponents are simply added up. With complex numbers written in their Euler forms, multiplication of complex numbers just got way easier, and I'm in an infomercial now. Now, like any other abstract mathematical concept, complex numbers are a theoretical way to model real-world things. What I'm trying to say is that it's really unlikely that you would be like walking down the street one day and you'd spot a complex number in the wild. With that being said, there are areas of applied math and physics where complex numbers are extremely useful. Anytime a signal is sent, like from your smartphone to a cell tower to your booty call, or from a radio station to your car, complex numbers are part of the unseen calculations. I hope this video has been fun for you and not too scary. Remember, multiplicative inverse, how it rolls off the tongue. Impress your friends, meet your soulmate, and until next time, keep it real or complex. Imaginary? Yeah, I need a better sign off.